So our next speaker, who's now emerging from the crowd on the stage, is Prof Arthur. Brian is another great innovator in science, as well as in technology, I would say. When he was in his mid-30s, Brian was the youngest professor to hold an endowed chair at Stanford. He was one of the pioneers of complexity, and in 1987, he became the leader of the first serious research program at Santa Fe, and it's a program that looked at complexity in economics. Later, Brian coined the phrase complexity economics, and that phrase lay dormant for a long time, but is now awakening as it is clear that economy needs a more realistic theory than the classical one. Brian received many prizes, but the one he treasures most is the inaugural version of the Lagrange Prize in Complexity Science, which he received in 2008. I know Brian since 2005, when I was setting up the founding conference of the Institute Paralimes in Europe. I had heard and read about Brian, but had never met him. And then all of a sudden the telephone rang. "Hi, I am Prof Arthur." The man on the other side said, "I heard you're setting up a European version of the Santa Fe Institute. I'm in Vienna at the moment and I want to be involved." Brian has become one of the inspirational sources of our young institute, and also now recently at the complexity program in NTU, and in the process he's become a great friend, and therefore it's given me great pleasure to give the floor to Brian.
I'm delighted to be here this morning, and thank you, Jan. I suggested a topic that's listed in your program, and I'm going to talk about something a little different. When I looked again at the program after I'd sent in my topic, I realized that this is about complexity methods. So I thought I'd better change slightly. And what I want to do is to give a kind of personal guided tour of agent-based modeling. And seeing that John Holland is here also, of my early involvement at the Santa Fe Institute and my involvement working with John Holland as well. And I'll say what John said at the start, about a third of you have heard a third of the story. So bear with me. Some of this material, much of it is new, and I've started to rethink agent-based modeling, at least thinking about it again, because suddenly, after lying underground, so to speak, it's become tremendously popular. And so has the work we did early on at the Santa Fe Institute. When I was a young, mostly mathematician and economic theorist, I had this dream that, in fact, when I was a teenager almost, I had this dream that it would be fantastic to be in somewhere like Göttingen in the 1920s when quantum physics was being dreamed up. And I realized, I was smart enough to realize that that would have been incredibly lucky. You have to be born at the right time, study just the right things at the right time, be in the right place at the right time. And then I went to Santa Fe, or I can say I was sent to Santa Fe like a pawn on a chessboard. Kenneth Arrow at Stanford stopped me and he said, "There's this little place you've never heard of in the Rockies, this little institute, it's just starting up. Do you want to go there?" That was 1987 in April. And I was at Santa Fe, and I'll tell you a little bit of the story as we go along. But I was there for 5 years, 10 years, before I realized that, at least in my opinion, hanging out with people like John Holland and Stu Kaufman and others, and really dreaming about how economics could be different and rethinking it. 5, 10 years later, I realized, oh my God, I was at some version of Göttingen in the 1920s where a field was getting rethought, and I was in the center of all of that. I used to think also it would have been fun to be at a Solvay conference. You see all these pictures of august figures, Marie Curie, Einstein, Bohr, and many, many others, Max Born. And I thought it would be fantastic to be at one of these scientific meetings. And maybe you'd have to live many, many lifetimes and just be very lucky for that to happen. But what I want to start with here is a meeting that was held in 1987 in Santa Fe, and I think it turned out to be just as historic as some of those physics meetings. I was put in a house rooming with a person I'd never met from University of Michigan. This was John Holland, and we were the first visiting scholars at the Santa Fe Institute. There's John, only a slightly younger version of John. And notice he has every bit as much hair these days as he had then, which is more than I can say. But at any rate, I was rooming with John Holland, and we did a lot of talking. It was a meeting that had been convened by Kenneth Arrow in economics, Philip Anderson, who's legendary in condensed matter physics, David Pines, many others. And in that room, among 20 people, were Stuart Kaufman, John Holland, Tom Sargent, who just got this year, a couple of weeks ago, a Nobel Prize in economics, Don Farmer, it was a stellar cast of people. It was quite staggering, and we were there basically to see how could we think of the economy as some sort of complex system or complex evolving system. I remember I gave the first talk there and I was extremely nervous and scared. These were super, super bright people. And the second talk, and this was in the early afternoon, was given by John Holland. We'd all come back from lunch. John started to talk about genetic algorithms. I'd never heard anything like that. John was talking about classifier systems. And I just sat there, absolutely enthralled and fascinated. And I had this very strong feeling that John was giving us the answer to something in economics. And all we had to do was to find what the question was. So John Holland was the answer. John's always the answer. The challenge for the rest of us is to figure out what question should we wheel up, because the insights are already there. So I wondered about this, and I thought, I have never sat through such a talk in my life. I was just sitting there. It's one of these things engraved in my memory. I remember where I was sitting. It was in the chapel of the old convent, if you remember, John, on Canyon Road. I remember where everyone else was sitting. It's like, you know, what happened when maybe, you know, where you were when Kennedy was assassanated. And I remember one really, really eminent...
They were really comparable events.
I remember one real hotshot young economist was fast asleep. I thought, God almighty, you know, here I am. I think this is John Holland bringing down the golden tablets, and this guy's completely asleep. Anyway, it stuck in my mind, and I wasn't quite sure why I was fascinated. So I went home and I began to realize that what John was really saying, John may disagree with this totally, but John could teach computer programs to evolve or get smart. In other words, John had the answer to something that we didn't have in economics. If you had agents in the economy, banks or consumers or producers, they didn't have to act and sort of walk in straight lines, this is what we can do, but they could get smart through John Holland's algorithms. And this fascinated me. And I went back exhausted about a month later to Stanford. I remember sitting in my office and I had this daydream my interest at that time was development economics, as we called them in those days, third world countries that now called emerging economies. And I was interested in how economies develop. How do they come out of nowhere? What starts an economy? And I began to imagine that with the help of John's algorithms, maybe, now I had an old Macintosh, it was a Mac Plus, this was 1987, 87. I was sitting in my office and I thought maybe kind of under glass, in a glass case in the corner of my office, I could have a computer, and in that computer would be a little nascent economy, and I would have little agents in the economy, maybe growing sheep, and then getting sheep fleece, and then there'd be other agents who were mining obsidian to make sharp objects with, and then maybe automatically using John's algorithms of getting smart, they'd suddenly come together and realize we can trade. And we can trade obsidian for sheep fleeces. And then I would go off and go to dinner and maybe come back the next day, and I'd suddenly find that they'd have little companies had formed and little firms, and come back a day or two later, maybe they had, by then, labor unions had formed, central banking had formed, come back 3 days later, there was some version of a financial district forming. All the smartest agents were going into the financial district and working there. No very productive work was getting done in the rest of this little economy that was developed. And the whole thing was crashing. So what I envisioned was the whole drama. And I have to admit, as a bit of a letdown, I couldn't see how to do it. Later, by the way, two very smart people, Josh Epstein and Rob Axtell, Rob's in the corner of the room, did manage to do something very close to this. It took several years' work, and it's very, very nice work, and it's written up, if you want a popular version, in Eric Beinhocker's book, The Origin of Wealth. But this was the dream, to ask the question, could I grow an economy inside my computer, get it to develop all these institutions, get it to develop economic structure, have the agents get smarter and smarter, and they would discover new things happening. All of this would be automatic. All I'd have to do is press the return button on the computer, walk away, and come back and see what had happened. Well, as it turned out, as I say, I didn't see exactly how to do that. But as the year passed and John and I were in more communication, I began to realize that there was something starting to emerge out of all this thinking. Now remember, this is 1987, turning to 1988. And there were a lot of simulation models around. They were equation-based. The whole idea of equation-based simulation is you've got all these buckets or categories, and the quantities go up or down like the amount of water in them. So many people are dealing drugs, so many cartels are forming in Colombia, so many of this, so many of that, and the whole thing is changing over time. And this seemed very good to us in social sciences, but it wasn't very good for producing new behavior. There was nothing that could come in from outside and surprise you, because these were just quantities that were going up and down like colored water in tubes or something. And it began to realize that what you could do with something like these algorithms, where you could have little agents that got smarter, we began to realize that we could model living, breathing, behaving individuals as little computer programs, each with its own computer program, inside our rather pathetic computers at the time, Macintoshes, or in a couple of years from then, Next computers, and each would be represented by its own computer program. When I was thinking about this, I realized that there isn't a time when this started. there isn't somebody who invented this. It came later to be called agent-based modeling. I think it was John Holland who called it that in 1991, but this was before 1991. What we were all thinking about, or a very small number of people were thinking about, was using the computer, and the people in the economy or in the problem you were looking at, each person, so to speak, each agent, would be its own computer program, and you can program that computer program to have certain rules. And several people had already done that. Some people had done it in their own minds. Some people had done it on computers by 1986, 87. So it had been thought of and done. But the ambition that John and I had was to go one step further than just have these individual artificial agents, as we came to call them, have simple rules. A simple rule would be, if an agent sees this, then do that. If the agent is in another context, do this. This seemed to be, to me at least, a little bit clunky, and we wanted to go a bit further. What we wanted was artificially intelligent agents, little computer programs that represented people really in the economy, somehow recognizing the situation they're in. How we were going to do that, I had no clue, but I was reading tons of cognitive psychology at the time and talking to colleagues in psychology at Stanford. And they would recognize the situation they're in, and somehow vaguely through the magic of John's ideas, these little agents would get smarter, and they'd learn, and they would adapt. And it became clear that as they adapted, they would change the situation they were in, and the game would get maybe more sophisticated, and they would have to change too. One of the things John and I used to sit and drink beer, if you remember, in the kitchen late at night. And John astonished me one time by, I was just blown away by many things he said. But he astonished me by telling me that a grandmaster in chess today could handily beat a grandmaster of 100 years ago. I said, I just flatly don't believe it, John. John says, yes. He says, grandmasters now have 100 years worth of experience, and they're much more sophisticated in given what they could see of who had done what in the previous 100 years. They had learned. But that meant that they were up against more sophisticated opponents than 100 years ago who had also learned. So the game itself had changed, and the agents, the grandmasters, had to get smarter and smarter to stay in the game, and that changed the overall situation or the game. And this is what we wanted to see if we could put in a computer. In other words, we began to learn or figure that what we could do at the Santa Fe Institute on our very small, as they were known then, personal computers, what we could do is have a little lab, and if there was a specific problem in economics, each agent taking part in that problem could be an artificially intelligent computer program that would learn better and better strategies. But that would change the situation, and everybody would have to learn better and better strategies. And what blew me away is that a system like that might never settle down. Now, we had had 200 years worth of economic thinking where all economists asked, where will the system settle down and be at equilibrium? In fact, that was the only question asked in economics in any problem. And here we were starting to look at systems that might never settle down, that would always be discovering novel behavior, that would always be discovering new strategies, and in the case of the economy, new technologies, new products, new anything. And it might never, ever, ever settle down. And, I had I was under a great handicap in economics. I'd been trained at what Paul Sappho called that other university across the bay, Berkeley. I'd been trained by absolutely superb theorists at Berkeley. So it was a bit like I had been trained in the Vatican as a Vatican theologist, say in 1520, and I was trying to grasp what Protestantism really meant. And I was under this handicap that I knew too much of the orthodox thinking. All of this left me absolutely again. Here's a problem. So we were trying to get these problems that would be great little labs where we could put standard economic problems into this lab, throw it into the computer, have our little agents get smarter and smarter, press the return button and see what would happen. Would we get anything different? Now I was inspired, coming from Ireland, I was inspired by a bar in Santa Fe on Canyon Road called El Faro. Apparently, I'm told it means the lighthouse or the lantern, El Faro. And
I always thought that was an Irish name.
yeah. And we would repair to El Faro of a Wednesday night. They actually, John had Irish music there on Wednesday nights. And a problem had occurred to me, you know, in between the beers at El Faro, and I want to describe it to you because it seemed to me just a beautiful little situation that could be put on a computer and we might learn something, and it would really, to use technical English expression, it would really put the boot into orthodox neoclassical economics if we thought about this. So here's the problem. The L for All problem, it got published, I published it in 1994. So here's the problem as I abstracted it. L for All's a really, really crowded bar with music on a Wednesday night. 100 people need to decide. This is like one of these bar stories. You know, 100 people walk into a bar and so there's a kangaroo. But 100 people are deciding each Wednesday whether or not to go to the bar on a Wednesday night. They all decide separately. And we will say they're all perfectly economically endowed with perfect rationality. They can do any amount of logic, and they're smarter than your average professors, even at NTU. These are not just super smart, but almost infinitely smart. What are they going to do? Here's the catch. This is really simple. The bar was crowded, and anytime there were more than about 60 people in that bar, you really didn't want to be there. You couldn't get a seat. It was horrible. It was sticky, and you couldn't sit down, and you just didn't want to go. But it took a bit of effort to go there. So I imagine that before anybody went on a Wednesday afternoon, they were going to say, should I go to the bar tonight? Should I go to El Faro? If it's really crowded, I don't think I should go. However, if I think not too many people will be there tonight, I'll go. I want to show you why this is a difficult problem for standard economics. Imagine you're trying to forecast, and this is the attendance in the bar maybe a dozen or so weeks. And last week we were 73. The previous week, 62 people showed up, 44 people showed up, 32 people showed up. Now, imagine you are these people thinking of going to the bar. They're all University of Chicago economists. They're all very smart, and they're thinking, okay, is there a logical way I can decide about going to the bar? Let's suppose we just use simple extrapolation. That's a logical method, and say 73 people went last week. Is that method going to be any good to say, you know, 73 people might go this week? Well, if everybody believes 73 people will go this week, it'll be crowded and nobody will go. so 0 people will go. If people say, well, all right, let's get really smart and say, many people will think 73 people will go, or a lot of people will go because a lot went last week, then they're not going to go. But knowing that people are infinitely smart and they're perfectly deductively rational, they will be able to do that logic and figure no one will go. So they will all go. But they can also do that second order calculation because they're infinitely smart. Knowing that they'll all go, then you can deduce that nobody will go. You can keep doing this ad infinitum. And the word I would use for this is absolutely diabolical. This is a version of the liar's paradox. If everybody believes that everybody will go, nobody will go. And there isn't a method you can come up with that everybody could share that would be logically validated, because if such a method existed, everybody would act on it and negate it immediately. So what really happens, and this struck me as a very good lab for thinking about how people really decide. What really happens in a case like this is people have very different ways of predicting. And what I did was to put this on the computer. I decided that each agent, each of the 100, be a little separate program. I wrote this in C. C was popular in 1992. And I created an alphabet soup of predictive methods. And I allowed, maybe I had 200 such little methods of predicting, very simple methods. And I allowed each agent maybe to have 5 or 10 chosen at random. So each agent could be different, and each of the little bargors could make up their own mind. And each of them would learn by using what was the currently most active or accurate rule, okay? So basically this was a bit like saying, real human beings don't think deductively. What they do is they come up with simple ideas, and if those ideas don't work, they chuck them out, and they use better ideas. I want to see how that would work out. Here's how it worked out, much to my surprise. I ran this on my computer, and you notice that it actually does settle down to an equilibrium, but with quite a lot of variation around that equilibrium. So the equilibrium is about 60. Some days it's a little bit crowded, some days it's not so crowded, but it actually did settle down. There was a very curious thing about this equilibrium. And this, I think, changed my thinking about economics. And that's this. That what emerged was an ecology of predictors. So if I was able to predict successfully what the numbers would be at the bar, I was predicting on an outcome that was the result of other people's predictions. So let me say that again. I'm trying to make predictions and choose the best predictor that I have at my disposal in a situation that's brought about as a result of other people's predictions. And this led, actually, George Soros has a name for this reflexivity. I hadn't heard of that then. But it's a self-fulfilling thing, or it's a self-organizing ecology of predictors. My predictions are only going to perform well in a system whose outcome is formed by everybody else's predictions. And moreover, it doesn't settle to an equilibrium. It's as if, on average, there are 60 trees out of 100 possible that are red rather than blue in this forest. But the trees that are red rather than blue keep changing. So here was an economics problem whose solution wasn't a single solution that, we all use the same strategy that will never change and be in equilibrium. The solution to this problem was an ecology, or a changing bunch of predictors that on average would give you this result at the bar. And for me, this was staggering. I sent the paper to a physicist friend at Santa Fe called Per Bach. You might have heard of him, self-organized predictors. Per faxed it to every physicist he knew, and suddenly the paper was famous in physics. That paper sat and sat and sat in economics. It was in the American Economic Review because I got it in without refereeing. It was at a conference proceedings. But the paper sat ignored in economics for 5 to 10 years. But it became really famous in physics. And now economists are sort of catching up to it. The reason is that not that economists are stupid, but this is very unfamiliar. That the outcome to an economics problem is not a solution shared by everybody, but an ecology that can change over time. Well, it's a no-brainer then to come back to thinking about financial markets. So to go back to, there I am in Stanford in 1988, wondering how do I get a little economy to develop on my computer? I couldn't see how. And in June 1988, I met John again. John had gone back to Ann Arbor. We met at a restaurant called Babes in, if you remember, horrible food, down in Canyon Road in Santa Fe. And I said to John, I can't do this developing an economy on a computer. I just don't see how to do it. But I've thought of a simple thing. Why don't we try and model a stock market on our computer? And I was going to say John could do all the programming. I discovered John was one of the top computer scientists in the world, but wasn't given to coding, at least not in 1980s terms. But we did get a lot of help, and John was very much behind the design of this thing. So let me tell you what's at stake here. There's a really brilliant economist, Robert Lucas, Bob Lucas, University of Chicago. In 1978, Bob Lucas cracked this problem in economics. It's called the asset pricing problem. It's basically, can you think of a solution, or can you model the stock market or a financial market and scientifically and reach a reasonable mathematical solution? Lucas's idea was to say, let everybody, is there a forecasting model? Now think of the forecasting model as a little plastic machine, plastic device. It's the same device for everybody and shows the same numbers for everybody. At the start of each day, you feed it in with numbers, information, could be the Wall Street Journal's fed in there, and the stock market, that little plastic model sitting in every trader's desk, tells you its forecast for tomorrow's price, and they adjust their portfolios accordingly. As a miraculous piece of mathematics, Bob Lucas was able to demonstrate that such a forecasting model exists. It would be in equilibrium, and it would be on average statistically upheld by market prices. The technical term for this is to say that there was a rational expectations equilibrium. If people are always rational, they will follow a forecasting model common to all, where that forecasting model leads to behavior in the market that upholds the forecasts, not perfectly, but statistically on average. It was a real crackerjack solution, beautifully done. Bob Lucas got a Nobel Prize for it a few years later. And I don't think it was that satisfactory, and I'll show you why in a moment. So here's the essence of Lucas's theory. So here's the little plastic model that's sitting on everybody's agent's desk, same forecasting machine for everybody. Feed it in with the market information, volumes, prices, past prices. So the same information gets fed into everybody's machine. It tells you what the price on average is expected to be tomorrow, Everybody puts in their buys and sells orders rationally as a result. Some market maker balances everything. New prices are declared, and everything's updated. This is called the standard theory of asset pricing or stock market pricing. And Bob Lucas's question is, what forecasting machine on average would be validated by prices? Well, in Faro, nothing was validated. If everybody had a common machine, as I just said, forecasting the attendance in the bar, that would be self-negating. So I was suspicious of this. I think Lucas's is a brilliant theory. What we tried to do in Santa Fe was just a slightly different version of this. Notice in the middle here, the only thing that's going to change is the box. So the information goes in as before, the market's made, prices are declared, but what really is different here is that all our little investors are not mathematical theorists. They are going to live inside a machine. That machine was sadly enough a Mac Plus sitting on my desk. And those agents would cognize the situation and then forecast a price, and they all would have their own ideas. In 1991, I'd been working with a team actually in the analytical group in Citibank in Hong Kong. We used to hang out in foreign exchange trading markets at 3 a.m. in Hong Kong, and I watched the traders. And I was impressed that the traders weren't doing rational anything. The traders were watching the prices, and the traders were forming hypotheses. Oh, I think the Central Bank of China has just come in. Oh, well, if they come in and then the New Zealand bank responds, here's what's going to happen. Or I noticed that the moving average has just crossed, or the price has just crossed the moving average of the last 10 days. I think people are going to notice that and buy in, therefore I should buy in. So actual traders, just like in the Faro situation, were forming little pattern recognition conditions that John just talked about, and then they were making forecasts as a result. So our idea was to keep the whole standard neoclassical apparatus, keep the whole thing that Lucas had done, and change just one thing, but it was the crucial thing right in the middle. We were going to change how the forecasts were made. All our agents would be allowed to differ, and they would bootstrap themselves up by having random forecasting methods or forecasting hypotheses at the start. And we fed them with market data, and they were able to have condition action rules. So our investors, and this was crucially different from the standard theory, our investors could get smart and learn. They were making a market, so the market wasn't of infinitely rational, identical agents creating prices that would be self-validating at equilibrium. This market was real, to be American I should say, real artificial agents in the computer, each with their own sets of ideas. But each of them had these little condition forecast models. Many of them, they might have 60, and they might be choosing among some of them. The typical one might be if the market has been going up the last 3 time periods, forecast that that the price will go up by 1.3%. Or if the market has been going down and the volume has been higher than such and such, and it is not the case that some other condition, then forecast a drop of 0.5%. Now, we created tons of these rules just randomly, just generating them at random, and then we let the system loose. As our agents went, they were able to figure out which models for them were most accurate, but they weren't stuck with those models. The non-performing models, each agent had a trapdoor, and every 10,000 periods, the non-performing forecasting hypotheses would just drop through randomly again, and via the genetic algorithm, they could generate new forecasting methods and feed them and try them. So this, for me, was much more human, much more realistic. What was the outcome? Let me say first what happens with Lucas's theory, or the standard theory. The standard theory is wonderful, meaning it's a wondrous machine of superb elegance, brilliance, and deduction, but embarrassingly, it doesn't conform very well with real markets. Yes, information moves prices, and if you compare reality with the standard theory, it actually compares very well indeed and passes a lot of statistical tests, and I think that's great. These are ticking boxes here. In reality, all traders would tell you that a market psychology exists. It's a bit hard to define, but it's basically saying people have very different ideas of what's moving the market, and that psychology keeps changing. The standard theory, by its setup, there's no market psychology. Everybody thinks the same. They're all infinitely rational. They all come to the same forecasting conclusion. They're all watching the same little forecasting machine. So there's no psychology. To go down here, and this is the most embarrassing thing about the standard theory, economists talk about it themselves, but they don't like to publicize it. In the standard theory, nothing is ever traded. There is no trading volume at all. And the reason is pretty simple. If you assume everybody's the same, they're all going to come to the same conclusions. It's assumed that price automatically adjusts. But if they're all on the same side of the market, they want to buy, there's nobody to take the orders and sell. So there is no trading volume. But miraculously, the price adjusts so that they're indifferent between buying and selling. It's a real embarrassment for the theory that there is a huge, huge, huge volume of trading every day, and theoretically there should be no trading at all. I can tell you this, that the derivatives market around the world, which Singapore should be very familiar with, becoming a real financial center here, the financial derivatives market is worth over $1 trillion, not per year. The GDP of the United States is something 14 or so trillion dollars per year. The amount of volume traded in the derivatives market is $1 trillion per day. So it's huge. Theory says it should be zero, if we're all infinitely rational. Technical trading, many of you know what that is, but basically it's the idea that past history of prices actually can help you forecast what the price will be next. It turns out statistically that's accurate. It's not a pipe dream. Work by Buzz Brock and others, Blake LeBaron, who was on our team as well, showed that technical trading is a statistical reality. That is, that past prices do forecast, albeit to a small degree, where prices are going to go next. In real markets, there's periods of huge volatility. We're in one of them at the moment, and then there's periods of quiescence. And again, if there's no trading, there can't be much of that. And as many people have noted, price changes have fat tails, meaning they look pretty normally distributed in the middle of the distribution, but occasionally you get these huge changes that people like George Soros can profit from. But again, that doesn't show up in the standard theory. What happened was we had a little meeting in Santa Fe when we were designing this, and we got a lot of help from Ramon Marimon, who's a Spanish theorist in economics, and from Tom Sargent. Tom is a colleague of mine, and Tom actually came out to give us a hand. It's the same Tom Sargent I mentioned, who got an economics Nobel 2 weeks ago. And we were literally sitting on different sides of the table. So John Holland and I are on one side of the table, Sargent and Marrimon, again I can remember the spatial distribution are on the other side. They're orthodox economists and really, really good ones. So they were giving us a run for our money. And they said, if you let your little agents do that experiment on your computer, nothing's going to happen. There'll be a lot of noise, but it'll settle down to the standard theory solution. Nothing's going to happen. And we said, we don't believe it. We think we're going to get pretty rich behavior, and we may even be able to replicate the behavior in the market. Well, here's what did happen. And the standard theory, yes, news moves the prices. Our price sequence, and I wish I could show you one, was very, very similar to the one that you get from the standard theory from real markets. So all that worked very nicely, but we got a psychology. We had a little ecology of different predictors, and our little agents were learning, and as they learned, that subtly changed the market. And as the market changed, then other agents had to relearn and readjust their forecasts. So psychology emerged, and maybe this is just being romantic, but I believe that at certain times our little agents were getting nervous. They might follow a trend upwards, and then you could see almost with red lights going on, some of them started to turn on predictors that say, if the market gets higher than 3 times fundamental value, forecast that there'll be a 20% drop next period. And you could see these predictors as if they're all starting to turn on. And our agents were able to hold both predictions in their heads at the same time. Expect it to go up, and expect also that there'll be a sudden inversion to the mean. And anybody in psychology will tell you, yep, that you get nervousness that things get really nervous. Not so much if people get a bad outcome, but people get nervous if they can go on getting a very good outcome, but there's a fair chance also of getting a horribly bad outcome, and you don't know which is going to happen. So in that sense, the psychology existed, or psychology comes into being. Technical trading came into being. We got little bubbles and crashes. And I want to mention this for a bit, periods of volatility. There's a technical phrase for this in economics. It's called Garch behavior. This is grad school stuff. Generalized autoregressive conditional heteroscedasticity. They don't give these Berkeley degrees away for nothing. Not like Stanford or I also have a degree from Ann Arbor. But that basically means there are periods when nothing much is going on, and then periods of quite wild behavior. I had a guy running this in Santa Fe, and I was able to phone him. I was back at my university then, and I could phone him every day or so and say, what's going on in our market? Oh, nothing much is happening. And he would call me, it's gone a bit wild. And the reason was, as I say, if some of our agents discovered a really smart piece of behavior to predict by chance, they're just lucky that randomly they'd come up with something that really worked, or they'd learned something and adapted better, then they would pile into that and buy far more of the equity or shares than they would. That would change the market, that would shift everybody else, and suddenly there'd be what in Santa Fe we began to call avalanches of change rippling through the system. Somebody changes, that changes the system, everybody else has to change. As everybody changes, everybody else has to change. And get these self-organized criticality avalanches just rippling through the market as they do in real markets. And then the game would go quiet for a bit again and nothing much would happen. I want to just say something here, and that is, we wrote this paper up in various versions. We did this work in 1988, 89. we perfected it actually over the next decade or so. We did it very carefully. We published a version in Physica D, I think Richard Palmer wrote that up on the team. And then we published a much longer, precise version in 1997. It was a strange paper. It was ignored by the orthodoxy in economics. And it was extraordinarily heavily cited. I took a look last night, pretty late. I thought, is this paper being cited much? I thought maybe it would be 50 or 100 citations. There are more than 1,000 citations to our paper. And the citations are all over the place. On the other hand, that thinking has still not penetrated the standard core of standard neoclassical economics. And I think it's not because the paper isn't good or the thinking wasn't good, or even standard neoclassical economists would say we're wrong. It's that it runs counter to so many traditions in standard economics that people just don't want to talk about it. You know, yes, you could walk naked down the street in Pall Mall in London, but if you do, we don't want to notice you're doing this. So it was it was regarded as very strange, and it's a mixture of being very heavily cited and regarded as a classic and ignored to some degree by the center. And I think that's true about basically of all changes in thinking, and I'm claiming this is a change in thinking. By the time we published this, by the way, there were many other people doing agent-based modeling, and the field had got a name by then. I want to just finish with some remarks here, and here's one objection. This is, shouldn't agent-based modeling in economics be stopped? After all, there's a famous law in economics, it's called Newton's third law of simulation, and it's every simulation is accompanied by an equal and opposite amount of dissimulation. The word dissimulation in economics means telling lies. So every simulation is accompanied by an equal and opposite amount of dissimulation or lie telling. But the basic objection, or one big objection that standard economics has, is if you could put anything into this sausage machine of agent-based models, and you could get out any answer you want. Well, yeah, you could put anything into standard theory, including that fairies are residing on the top of the Empire State Building, or dancing on the Henley, or something like that. And get out the idea that markets shouldn't be regulated. So that sort of thing happens in standard theory. What we need actually is a rigorous, replicable set of models where the assumptions are very well stated and anybody can replicate and object to the assumptions, and maybe to the process as well that's assumed. So I think that the moral of this story is that rigor is needed and replication is terribly important. Again, the way to think about this is a lab that's computer-based, and you can conduct experiments in that lab, but those experiments better be as rigorous and as well-defined as they are, say, in molecular biology or in any other field. Another one, is this really theory? I love this one, because I'm a theorist, and I can get really good theorists maybe come to Santa Fe, and then you explain all this to them, you show them these models. It's beautiful. And there's a pause always. But is it really theory? And I have a couple of answers to this. In economics, actually, most economics up until 1920, all of economics was wordy. A little bit later, it was based on diagrams, maybe by 1860s, 1870s. A little bit later, it started to be based on algebra. A little bit later, it started to be based on calculus. by the time you come into the 1960s, it's based on differential topology, and now it's based partly on computation. Every single one of those techniques and methods was bitterly opposed at the time. There's a famous saying from Max Planck, science proceeds funeral by funeral. So I would say any new technique is suspect. In 1610, Galileo manufactured his own telescope. He heard about telescopes, Dutch invention. Galileo produces a really good telescope, points it at Jupiter, and there's a kind of oh my God moment. Oh my God, there's satellites, there's moons orbiting Jupiter. Oh my God. And he was kind of blown away, December 1610. In fact, he would up night after night and he thought, am I seeing things? This is ridiculous. But they kept appearing. So, of course, he did the scientific thing. Within the next month, he invited learned professors up to his rooftop at night, and they all peered through the telescope, and they were able to come in successive nights and see that these dots had shifted. But there was a big objection. How do I know these things exist? What really exists is what you can see with the naked eye. If you can see it through your contraption, Mr. Galileo, these could be motes in the eye or aberrations that are part of your contraption. So we can't really say these things exist. You haven't followed the rules. The rules are that they exist if you can see them with a good sharp eyesight. That's the gold standard. And Galileo couldn't prove that. So it took the younger generation for this to catch on. Let me just finish here with a couple of observations. Eric Beinhocker wrote an excellent book in 2006, and I'm just commenting really here on what's happened in economics. And Eric talks about the radical remaking of economics. I do think over the last 3-4 decades, there isn't a sudden remaking, but economics is starting to adopt more and more and more realistic assumptions and get away from its theological assumptions. Assume everybody's perfectly rational, assume this, assume that. That isn't true in reality. And so we're getting much more realistically based economics. Part of that is agent-based modeling. But agent-based modeling, there's plenty of room for bad modeling. There's plenty of room for sloppiness and laziness. And so what has to happen here is rigorous testing and rigorous thinking, and then good rigorous modeling. And I think economics is changing. It's greatly helped by the crash of 2008. The Economist magazine said the economy wasn't the only thing that crashed in 2008. Standard neoclassical economic theory also crashed too. And I must say I was very pleased about that. Finally, I want to say that this is part of an overall revolution that's sweeping through all the sciences and mathematics too. Computation is changing everything. To go back to telescopes, in the period of optical telescopes, which runs right up to the 1950s and beyond, the improvement in resolution was about 2 to 3 orders of magnitude, somewhere around 500. So you can see 500 times more accurately than with the naked eye with telescopes from Galileo's day to Mount Palomar. From about the 80s on, we get computation improving our eyesight through the telescope. And I thought, well, computation might improve that maybe by another factor of 2 or 3 or something. It doesn't. It improves it by a factor of about 3 to 4,000 again. So the telescope gives an improvement in astronomy of 10 to the 2 to 10 to the 3. A further improvement of about 10 to the 3, 10 to the 4 is possible via computation. And rather than saying about the wonders of computation, doesn't. It's not agent-based modeling computation, but it's the use of the computer. There's a nice quote, and this is from Greg Chaitin, who's a mathematician, and I like this quote. I'll finish here. Computers are changing the way we do science completely, and mathematics too. The computer can provide an enormous amplification of our mental abilities, and it's really changing the way everything is done. No computer, no genomics. It's that simple. No synthetic biology. Nothing is possible without the computer. You can only understand something if you can program it. And that is a simple and non-intuitive and deep statement. The computer is a lab for mathematics the same way that the physics lab is the empirical content for physics. And this is Greg Chaitin, who's a first-rate mathematician. Well, I'll stop there, and thanks very much.
Very much, Brian. The rule of the game is that we stop at 11:15 in order to mix with the other group. So since 11:15 has already passed, I think we should, anybody that has questions to Brian should ask them anywhere else during this workshop, but we have no time for questions now. So I think we return in half an hour, is that right, Tesla? Yeah? Okay, so in half an hour from now, please come back.